Hello everyone. So today we will be discussing Terzaghi's bearing capacity theory. So for that, the approach that we will be taking is the limiting equilibrium approach. Okay, this is the situation when we balance the forces when failure is about to happen. You see, what are the two types of forces that exist? One is the force that causes the failure, and another is the force that resists the failure, isn't it? So if we balance those two forces, that means the causative force and the resisting force, then there is the equilibrium condition that is achieved. So we'll be taking into account that situation for analyzing Terzaghi's bearing capacity theory. Now these are the assumptions that we take while discussing the Terzaghi's bearing capacity theory. Okay, first is that we consider a straight footing. Okay, we consider that the footing is a straight footing. This one. It means that the length of the footing is much greater than the width. Okay, so that is one condition. Now, second one is that the base of the footing is at a shallow depth. Okay, that means whatever is the depth of the footing from the surface of the soil, that should be less than the width of the footing. Okay, so if we consider that this one is the footing, in this case, this is for condition number 2. If this is the depth of the footing, okay, this is the top surface of the soil, and this is the base of the footing, okay, this is the depth, and this is the width of the footing, then depth should be less than the width. Okay, that means if we divide depth by the width, we get the value less than 1. So that is one thing that you should know. Next is the third one. Sharing resistance of the soil between surface and base is neglected. That means we neglect the resistance of a soil which is located here. Are you getting my point? From here to here, this is the top surface of the soil, this is the base of the footing. This part, when you consider this soil which is in this location, we don't consider the resistance given by the soil located here. We consider the resistance given by the soil which is located beyond this part. That means whatever soil is there which is located below will be giving the resistance. Okay, then we consider that the failure is number 4. We consider that the failure is happening according to general shear failure. So there are basically 3 types of failure. One is general shear failure, one is local shear failure, another is punching shear failure. So we will go into details, okay, of each of them. Now, general shear failure is a type of failure where, if you want to understand it for the time being, it is a failure where the failure planes are well defined. That means when the soil is failing, the planes by which the soil will fail can be well defined. Okay, so now we will be drawing a condition where the general shear failure, all these things will be shown. Okay, so here we can see, suppose this is the footing, okay, and the load falling is Q. Okay, and then these are the points you can see A, B, then D. Then you see when the load is applied, then 3 zones are created in the soil. One is the zone 1, okay, zone 2, and zone 3. Okay, so let us discuss what are these zones. Now, zone 1 is the zone where the soil is assumed to be a part of the footing itself. That means this part is considered as attached with the footing. This part is considered as a part which is attached to the footing. It is a part of the footing. Okay, it is not considered as a separate entity. It is considered as a part of the footing. Now, why? Because you see, the base of the footing is rough. Okay, and it is assumed that it is rough, and there will be friction between the soil and the base of the footing. Okay, and this soil in this zone 1 cannot go in any lateral direction. Okay, and so generally this gets attached to the footing itself, and so it is assumed to be part of the footing. Okay, and it is also said that this zone 1 is in elastic equilibrium. Okay, now what is this zone 2? Okay, so zone 2 is a zone of radial shear. Okay, and if we look into zone 2, we can see that the shear planes will move like this. Okay, and zone 3 is the zone of linear shear. You can all write this down. Okay, so zone 2 is the zone of radial shear, and zone 3 is the zone of linear shear. Okay, and this angle of failure in this zone 3 will be 45 degree minus phi by 2. What is phi? Phi is the angle of internal friction. Okay, you can write all these things. Okay, so phi is the angle of internal friction. Now, how do we find out QU? What is QU? It is the total load intensity. Okay, that is falling. Okay, so for QU, you have to balance the forces on the triangular portion, okay, or the triangular wedge. So this one, we will be doing the balance of forces here. That means we will be using the condition of limiting equilibrium, where the forces which are causing failure in this region, the forces which are causing failure will be balanced by the forces which are resisting the failure. So for that, what we have to do is, let us go into this portion in a very detailed manner. Okay, so now we have modified the diagram a little bit to understand how to find the equation ultimately, which will be the Terzaghi's bearing capacity equation. So now you see here the width of the footing is B. I'm just drawing it separately here also. Okay, so width of the footing we consider B. Q is the load intensity. Okay, ultimate load intensity that is falling. Okay, so overall whatever load is falling, okay, that will be termed as QU. Then W is the weight of the soil. Okay, W is the weight of the soil, which is in the triangular portion. All right, so now if you want to first find out the forces which are like causing the failure, what will be the forces? One will be QU, okay, and another will be the weight. Okay, so that are the forces which are causing failure. Now QU, what will be the force? This is the force load intensity. Intensity into area is the force. Now area, we have taken the width as unit. Okay, so what will be the force for QU? it will be, isn't it, intensity, load intensity into with this B into unit weight, unit thickness, you can say. So that will be what, the force. Okay, so that is one we have got. Then what will be the formula for the weight, for the weight W? So it will be how much? So now for that we need to first consider the unit weight. Okay, unit weight, if we can find out the unit weight and the volume, suppose unit weight is considered as gamma and volume of this we can find out, then multiplying it we can find out the weight, isn't it? So volume will be how much, area into thickness. So thickness we have considered unit. Okay, so now area, how will we get? You see, if we consider this triangle, okay, then what happens is, in this triangle the width is b, so half of it will be b by 2. Then this is phi, we told you, which is the angle of internal friction. Then if we consider this portion on this triangle, of this whole portion I'm considering this, how much it will be? If we consider trigonometry, it will be b by 2 10 phi. Okay, so if we want to find out the area of this part only, okay, what will be the area of this part? Isn't half into base into altitude? Okay, so it will be how, b square by 8 10 phi. So that is the area of one part. So if I want to find out the area of the whole, it will be how much? 2. That means b square, ultimately it will become b square by 4 10 phi. Okay, so b square by 4 10 pi we have got, that is the area. Then if I want to find out the volume, this area into thickness, unit thickness, so it will be what, same, b square by 4 10 pi. So volume we have got, then weight will be what, gamma into volume, it will be, so this is the formula for the weight, and this is the formula for the what, total load, okay, which is falling from onto the soil surface. Okay, at this level, what is the total load that is falling on this level is this one. Okay, and the weight of this is given here. So these are the forces that are causing the failure. Okay, now what are the forces that are giving resistance? So there will be two forces that we will be considering. One is denoted like this one. one is the passive resistance, which is given by the zone 2 and zone 3. Okay, the soil that is here are what? Zone 2 and 3, isn't it? So pp is the passive resistance. When you see, when the load is being applied, the whole mass is going down. Okay, so the forces that were causing the failure was this load plus this load. Okay, because this is considered as a part of the footing. Okay, so whatever weight is here, that will be the force causing failure only, because this footing load, whatever load is there, and this load will be the disturbing force causing failure. And whatever soil is there outside zone 1, zone 2, zone 3, we have discussed, isn't it? So they will try to resist it. So first of all, the resistance will be given by the passive resistance pp, okay, on both these sides. And also there will be cohesion. So at this surface there will be cohesion, so cohesion will also give a resistance. Now if we consider a normal to this plane and this plane, this angle will be angle of internal friction, because you see the soil here and the soil here are same. Okay, so angle of internal friction here also will be same as that of the angle of internal friction here. Soil is same. Now angle of internal friction is what? Generally it is the angle between the resultant and the normal. So resultant force, whatever is being applied by this soil in this region and this soil in this region, is pp, and the normal is this one. So obviously angle between it will be angle of internal friction. It is the angle between the normal and the resultant. And again, since this is the plane of failure, there will be cohesive force which will be acting tangentially. Okay, so that is also that will also be giving some resistance, and this cohesive force will have a component above. Okay, you see this qu, this is what? This is the disturbing force causing failure. Okay, okay, so this is going vertically, so this pp is also giving a vertical reaction. Now cc will also have a vertical component. This c cohesion will also have a vertical component. So we need to find out the vertical component of c. What will be the vertical component? This will be c sine phi. Okay, so the vertical force going down is this one, and vertical force going up will be p and c sine phi, c sine phi. So now if we balance it, okay, since it is the limiting equilibrium condition, let us write down the equation. Isn't it? These are the forces going down, and these are disturbing forces. These are the forces going up. They will be resisting forces. So ultimately this is the equation for the limiting equilibrium. Now this pp, it consists of three parts. One is pp gamma, another is ppc, and the third one is ppq. Okay, and they are related to various components. Now pp gamma is related to, you can write it down, it is related to weight of the soil in the shear zone. Okay, and in the zone 2 and zone 3. Okay, all right. So zone 2 and zone 3. Now PPC is related to the cohesion of the soil. And PPQ is related to the surcharge. You see, the weight of the soil in zone 2 and zone 3 will be offering resistance, which is and which will be denoted by PP gamma. Cohesion of the soil will be offering resistance, which will be denoted by PPC, and the surcharge is this one, DF. This DF, in this depth of DF, there is a soil which is giving a weight. Okay, and that weight is transferred to zone 2 and zone 3, which is located here, and ultimately they will be offering one resistance which will be considered as PPQ. Okay, that is, this PPQ is related to the surcharge. Okay, so you have to remember that PP is consisting of three parts. One part is related to the weight of the soil in zone 2 and 3, one part is related to the cohesion of the soil, and another part is related to the surcharge. Surcharge is given by the load of the soil which is in this location. So we can now modify the equation. Now how will it look like? We can write it like this. Now this cohesive force, C is the cohesive force, isn't it? Force is equal to stress into area. So let us consider the cohesive force is equal to stress is equal to small c. Okay. And area. Okay. So see, there are two areas. This small c is applying on this area, and this small c is applying on this area. So let us calculate it for one, and we can find it for both. Okay. And just multiply it by 2. So for this area, let us consider it will be how much? Area is how much? C is, small c is applied here. AD is this one into the area here will be this length into thickness. It is unit. Okay. Now again let us draw this triangle. We can write it like this, isn't it? Because if this is the triangle, okay, half of the triangle I'm taking, so b by 2 AD cos phi is equal to base by hypotenuse. Okay, so what can we write in place of AD? We can write it like this. So this AD uh, will be equal to b by 2 cos phi. Now concentrate on this term. Okay, twice c sin phi. Isn't it? C into AD, we can write small c into AD. This was the cohesive force, this was the cohesive stress into area. We can write, in place of AD we can write what, B by 2 cos phi, this one. We can write it. So ultimately we can modify it in this manner. Okay, so till now I hope you were clear with it. We have modified this equation, okay, using this concept. Now please go through this um, discussions all over again. Okay, if you are like satisfied with the way the class has progressed, please comment today. Okay, and then I will think whether I will proceed or not. Okay, please do it. Please give me your feedback. Okay, if you think that it is good, then I will keep on making classes for Geotech for the next 4 to 5 days. Okay, thank you very much and stay safe. Okay, thank you.